And we are recording. So welcome everyone. Today we have Vincent Wan from TI presenting his session and talk on power management on Zephyr. Take it away, Vincent.
Thank you, Vicky. So hi everyone. Today I'd like to talk to you about power management on Zephyr. Over the past few months, I've been working towards adding power management support for the TI CC1352 onto Zephyr. And I'd like to share with you some of the things I've learned. So Zephyr is a real-time OS that focuses on connected resource constrained devices. And resource constraint here includes constraint on power consumption in many cases. And Zephyr has an existing power management subsystem to deal with that. And as of Zephyr 2.20, the features that are supported, they're mainly divided under two separate knobs, if you want. There's the system power management and device power management. Under system power management, the focus there is to define sleep and deep sleep states that be entered when the CPU is idle. And how the system decides which state to go into is via a power management policy function that is residency-based, meaning that it would pick the state that has the highest latency that would match up with basically the amount of time till the next system deadline. And the idea there is that by picking the high latency state, that means we're in the deepest state, deepest sleep state, which means we save the most power. And the subsystem also supports the power state locking feature, which means that the application can tell the policy, okay, I don't want to enter certain sleep states, so please don't go into them by locking these states out. And also there's the ability to force a power state, basically by initiating that state while the CPU is active. So you can think of that as when, say, you want to initiate a shutdown, for example. And then there's device power management, and there the scheme that is used called centralized method. Really, what that is before the CPU goes to sleep or deep sleep, it would notify all the device drivers on the system, or basically telling them, okay, please low power or suspend the device that you're managing. And then the drivers would do that. And then when the CPU resumes, then it would tell all the drivers to bring the device back to active mode. It's a simple scheme, and there's an alternative in the documentation in Zephyr called distributed method, but I don't see that being implemented in the code base, so I left that out of the slide. And then there are two other features here that I'll touch on later on in the presentation. On top of these, there's also something called tickless kernel mode that Zephyr supports. And what that is when Zephyr, when the CPU is idle, it will program up the system timer in such a way that it wouldn't wake up the CPU until the next system deadline, as opposed to waking it up periodically, and then for the CPU to find out, okay, it has nothing to do, so I'll go back to sleep and waste power that way. So there's a brief overview, and if you like more on these, go to the Zephyr documentation and check out the source code if you like. So here's the board that I have been working on. This is the CC1352R1 Launchpad. And the device that's on there is a ARM Cortex M4F running at 48 megahertz, and it consumes roughly 3 milliamps while active. It supports 3 low power modes: idle, where the CPU and the RAM is clock gated, so it has very low latency. And then there's a standby mode where the CPU has retention, so it knows where to resume once it comes back up out of sleep. And in that case, the real-time counter or real-time clock on the device is left on. But other than that, all the other peripherals are turned off. So it's a fairly low power mode. And then there's also the shutdown mode where really everything is off except for the I/O being latched, and it's ready to receive input from external events, such as a button push, for example. And here's the implementation. The user application called is Zephyr. And then Zephyr has a bunch of drivers, the power policy, and SOC definition, where it knows how to initiate the various sleep and deep sleep states. And these would call into something called the TI hardware abstraction layer for support. And it in this hardware abstraction layer, or HAL, there's a TI power manager that I leverage more substantially. And in there, there's a function called power sleep that I use for initiating the standby mode. There's a feature called power dependencies that basically turn on and off peripherals and power domains, depending on whether they are needed or not, by reference counting them. The feature refer to these as being resources. And it's a nice way to automatically do that. And then there's a feature called power constraints, which is not essentially needed because it's identical to the power locking mechanism in Zephyr. However, we anticipate bringing in some TI drivers, such as the TI RF driver, which leverages this this feature. So I left that in there and made sure that the power policy supports this. And then there's a power notification feature, which allows the drivers to register a callback function with the power manager, so that when the device wakes up, it can be notified of that event, and it can go ahead and reinitialize the peripherals if needed. And this is because in the case where system power management is turned on, but device power management is not turned on, then the device drivers are currently not notified of these wake up events. And I'm sort of leveraging this to work around that fact. And the power manager leverages the device porting layer, the DPL, for some basic timing and interrupt support, along with this TI driver library, which has some basic function to access the registers on the device. So that's the picture. And now I'll just walk you a little bit through my journey. So I first added a timer driver that is based on the RTC, because it has the ability to wake up the device from standby mode, as opposed to the standard 6-tick timer that's on the M4, which doesn't have that capability. And as part of that, I'll make sure that it supports the tickless kernel mode, so that we can leverage that. And then I map the sleep states to the supported power modes on the device. And Zephyr supports up to 3 sleep states and 3 deep sleep states. only needed 3 total. The mapping is pretty straightforward, except for the fact that standby mode is kind of like an in-between thing. So it power gates the I guess most of the device down. Uh, so that makes it more like a deep sleep state, according to Zephyr's definition. But at the same time, it resumes from where it left off. So that makes it more like a sleep state, according to Zephyr. Uh, in the end, after some discussion on GitHub, I opted for it to be a sleep state because of that nature. Um, and then I initialized the TI Power Manager during system initialization in Zephyr. And after that, I created a customized power policy function that is residency based as well. And the reason I don't want to use the default one is because I only want to enter sleep states, but I don't want the device to shut down automatically for me while the CPU is idle and then lose the CPU state. I also check any power constraints set by TI drivers to support that feature. And I also schedule a K timer to wake up just slightly ahead of the next system deadline to account for any wake up latency so that we really do meet the deadlines. And then I implemented power management in drivers. And first I had to define a list of core devices. And what core devices are just devices that would be power off last before going to sleep and power back on first after resuming. And these are typically things like system timer and the UART to support timing and logging services for as long as possible. And then I enable all the I/O pins as wake up sources in the GPIO driver. I guess primarily because this is also how TI RTOS does it. But in addition to that, Zephyr currently doesn't have a formal mechanism to define wake up sources. And then I implemented a PM control function in each driver to handle the low power, suspend, and off states. And I handle them all in the same way because these devices only have on-off state. And then I had to lock out the standby mode whenever there is an ongoing transfer in these drivers. And as part of doing that, I found that the UART driver API is not super power friendly. It has support for a function called UART PON, which basically expects the UART to be on at all times, so that whenever the function is called, it will just pick up the next character. So it's very difficult to lock out the standby mode in the driver when it has that expectation and the application can step in, which means that it's not as user-friendly. And then the last point I've already touched on earlier. So here are the two features that I skipped. So there's this device-based indication under device power management. And that's used to indicate that the device is busy. And this is pretty much very similar to the power state locking mechanism. I found it to be actually more useful because it has the ability to specify, okay, I don't want a specific sleep state. I don't want standby mode, so I can say just lock out standby mode, which is this feature is not doesn't have the ability to do. And in addition, I don't see the PC status being checked anywhere in the code base in Zephyr. So you can start it all day long, but if it's not being checked, it's not very useful. So maybe it's a feature still under development, or maybe there needs to be an example to show me how to use this. And then there's a device idle power management. That's pretty much similar to the power dependency feature in the TI Power Manager by adding a reference count to each device and then turn the device off when the count is 0. Unfortunately, it did not work very well with the centralized power management method because when the CPU resumes from, say, standby, then it would go and try to reinitialize and repower up all the devices and all the drivers, regardless of what the reference count is. So it doesn't check that count currently. So there's some integration issue there. And also it doesn't have the concept of power domains. And sorry, I forgot to define power domains earlier, but power domains are basically partitioning of the device that can be turned on and off as a whole together. And because it doesn't have this this concept, it was better to make use of the TI Power Manager instead. So in order to make sure that this works, I did some power measurements using the technology from TI called Energy Trace. And what that is TI has added some extra emulation hardware on the board to allow us to measure the current flow to the target and digitize those measurements and then provide some software tooling on the host side to retrieve these measurements automatically. And it has an accuracy of roughly 0.5 microamp in this case, a range of 1 microamp to 100 milliamps, sampling rate of 256 kilosamples per second. And all these measurements I took were averaged over 10 seconds worth of samples. And here, if you look at the first scenario, it basically corresponds to standby. And in Zephyr, I was able to measure roughly 1 microamp, which is in line with a nominal figure. And when I compared with TI RTOS, I could see that it was roughly the same. So that is good. And that should be expected because we are using TI Power Manager for this. And then I tried to run Hello World and printing out once a second, and then going to standby in between. And under Zephyr, that came out to about 12 microamps. And that's slightly higher than TI RTOS, but that's to be expected because ultimately we're using 2 different UART drivers here. And the UART driver in Zephyr is not as efficient currently. I believe it uses polling and it doesn't make use of any buffering in the UART peripheral. So some indication of some optimization that could be done there. And then the next 2 scenarios are basically just examples taken from Zephyr, mainly just to show what kind of power consumption we get when SPI and I2C are being used. And then in the last scenario, the shutdown mode, the consumption was too low for me to measure with TI Energy Trace, so I used that old-fashioned multimeter and hook it up to the power rail to the target, and then the numbers came out not too far from the nominal figures as well. So I know that Kumar and others have some interest in seeing a demo of any TI Energy Trace. So I'm going to show you that. I believe we still have some time. So so here's my setup. So I have a Dell laptop running Windows and connected to the board. And what I want to show you is STune, which is a command line utility from TI Composer Studio or CCS, and it basically has the ability to pick up the power measurements. And then I want to show you Energy Pi, which is a bunch of Python wrappers that some interns helped us write some time ago. And I was able to dig those up from our servers. And they invoke STune and XDS DFU utility, which gives access to some of the emulation capabilities on the device. And basically, it's basically able to bring all of that data into Python. So let me first show you STune. So here I am in the STune directory in CCS, and I type STune. That brings me into the shell of STune. And let me connect up the board here. Here we're actually measuring something. So currently, I preloaded the hello world scenario on the target, and I like to connect to the board. So I'll connect using this dash C option, using standard CCS configuration file, and connect to it using TI XDS emulation. And then after that, I want to run the energy trace command over 5 seconds or 5,000 milliseconds, and send the output to this CSV file and measure over the 1 microamp to the 100 milliamp range, and use the standard energy trace mode to do that, which I found to be more accurate in this case. And it's currently running. It's stopping after 5 seconds, and we should be able to see the measurement in a bit. It takes a little bit of time to compile that CSV file. So here it is. So 5 seconds, and it shows the average maximum and minimum current consumption, and also the total amount of energy that was consumed. And let me show you this CSV file. Let's see. So I'll put the CSV. It produced 2 files because it actually chunks them up into 4-second periods. And here's the data. So you can see the timestamps, you can see the voltage, which is constant, and then the current measurements and the energy measurement. So it'd be nice to be able to say plot some of this, and that's where Python comes in. So let me just reset the board to make sure we start from a clean slate. So here we're in the Energy Pi installation directory, and from here I like to run this Python script that I wrote, demo.py, and then pass it the executable that I want to measure. And while it's running, let me show you what's in the script and in the executable. So the script is very simple. It basically creates a board instance from NGPy, and then it flashes the binary to the board and resets the board, and then perform power measurement using STune. And it collects the data into this EP data variable, and then it basically plot it using a popular package in Python called matplotlib. And then let's look at main.c. So in the application, first thing I did was shut down the external flash on the board that is automatically powered when the board is connected. I don't really use this flash for this application, so I don't want it to show up in the energy measurement. So I turn it off. And then I set up the GPIO for a push button that can be used to wake up the device if needed after it shuts down. And then I busy wait for 5 seconds. After that, I sleep for 2000 microseconds, which is 2 milliseconds. And that's a very small amount of time, which means that the power policy function would pick the idle mode in this case. After that, I sleep for 3 seconds, which is longer, and the power policy function would pick the standby mode in this case. And after that, I forced the deep sleep state number 1, which corresponds to shutdown mode, and shut down device. So with that, I believe the script is done, and here's the graph. So yeah, my machine is a little slow. Well, there you go. So as you can see, the first chunk here is basically when the device is busy waiting. And you can see that only a little over 3 seconds of it, because there's a delay between when the program starts and when the measurement actually starts. So we don't see all 5 seconds of it, but that's where the busy waiting happens. And then we see a transition. And if we zoom into the transition, we can see that, okay, it dropped briefly into idle, which is where it consumes roughly a little less than one milliamp. And then it goes back up active before dropping out off into standby mode. And let me zoom out. And basically, we stay in standby mode for 3 seconds. So from 3.2 roughly to 6.2, we are in standby. And you can see these spikes here. These basically recharge pulses while the device is in standby, because the CPU still has retention. So there needs to be some power for it to retain that logic. So that's what these are. And then after the 3 seconds are done, then we wake up, and then we force the shutdown mode. And you can see that after we force the shutdown mode, then not much is happening after that. So you can kind of see the possibilities here in terms of graphing and analyzing this measurement data. All right, so just let me wrap up here. So in summary, Zephyr provides a basic power management framework, and with the help of the TI Power Manager, was able to get decent results in the static scenarios that I've measured. And both system and device power management support for the 1352 have been merged, and the shutdown mode support is still pending review. And in general, I just say that the power management subsystem could benefit from more features and just better integration between the features and also between the features and some of the aspects like device driver API, for example. And I believe it's encouraging to see all the brainstorming that's been going on Light. So it'll be very interesting to see what happens down the road. And that's pretty much all I have. Any questions?
Okay. I had a couple questions. I was taking some notes, or Vincent. 0.85 microamps. You retain all the 80 ks RAM. That's an impressive number. It's not a question, just a comment. Just looking at my notes. What
Thank
do you
you.
mean when you show those power numbers? There's a footnote that says external flash off. What do you mean by that? I assume external flash, like that's SPI flash or something, or QSPI flash, not the internal flash memory.
Yeah, so there's some external flash that is sitting on the launch pad itself.
Oh,
That is not part of the device, and
okay,
it the device communicates to it via SPI,
yeah.
and this flash is automatically turned on when the board is powered up, um, and the power consumption of that flash shows up in the measurement. So I had to turn that off in order for it not to dominate the measurement, especially in the cases. So I have very low numbers, like in standby mode, for example. Um, it would it would pretty much you know,
Yeah,
maybe like
ruin
make
numbers.
the measurement like 10 times what it is.
Yeah, yeah, of course, I understand. It's the same with putting your pins. If you have pull-up resistors or things like that, you want to set them before you go into deep sleep. Um, I was thinking, what my concern would be, let's say we want to, how to frame this. The question was clear in my own head. Well, I was working on a driver for a demo a couple of weeks ago for an embedded world demo that I've still been poking around it. And it basically has a set of sensors. They treat like a spectrometer, but it takes me about 1 second to get a sample from the sensors. So I'll start the I squared C transaction, and then I just have to wait like 800 milliseconds before my sample is ready. I guess this comes back to, you were saying that we don't use like the device tree busy flag at all, but how in your opinion, in a sensor driver or a device driver where we know we need to stay active for 800 milliseconds before we can go to sleep, is there a way to indicate something like that, that in Zephyr, in the power management library today, like let's say I get a call back to say, okay, time to go to sleep. Can a sensor driver say, oh, wait, hang on, I'm waiting for a result and I need another 200 milliseconds?
Yeah, I believe that can be done using the power locking feature. Uh, Basically, you call an API before the sensor starts the transfer, and to tell the power policy, okay, I need you to not go in this sudden sleep states. Um, and then when the transfer is over, you can unlock that state. Um, that means the CPU will be able to enter that state and continue on to save power.
Okay, that makes sense. What else? Dun, dun, dun. Yeah, I guess I was curious, and this is just me putting my let's make things complicated hat on. Is there any sort of timeout, like with a driver? Let's say I tell there's a system event where I say enter a specific sleep mode, and then that will send a callback to other drivers. But do you have to get a response back, or is there some sort of timeout? Like if a driver just doesn't respect something and doesn't go into low power mode, or is there any sort of
Yeah, currently the scheme is fairly simple in Zephyr. It just basically call a function each driver to tell it to either go into low power mode or suspend state, and and then the driver would then initiate the device off sequence and bring the device off.
okay,
And then
there's no
when the CPU comes back on, it would reactivate all these devices. Uh, so if you need anything beyond that, then it would be part of the application or
okay.
part
I'm
of the
just curious
drivers.
if that process is really slow. Like maybe it takes like 500 milliseconds to shut something down if there's like a motor you need to stop or something like that. I was just curious what, I mean, I'm making things complicated, but maybe just something to keep into mind where you can't just stop a motor instantly. Before you go to sleep, you'll have to sort of
Mm-hmm.
roll it down in terms of slowly decrease the
Yeah,
speed.
yeah, definitely. That the latency can be an issue if the peripheral that you're dealing with is slow. Uh, you might be waiting a long time for it to shut down. Uh, and that is certainly a concern, and that is why the latencies for each sleep and deep sleep state is programmable, so it can be configured as part of the keyconfig mechanism in Zephyr.
Okay.
And so if you have a motor and it takes, I don't know, maybe like 1 second to shut down, then you can set up that latency to be a little longer, and then account for that while the so that the power policy would know, okay, it takes 1 second to go into this sleep state, so I only have 750 millisecond till the next deadline, so I better not do this. So it would just not go into that state.
Okay, that's good. That's good that somebody's thinking about that. Then I'm quite ignorant about the power management system today, and that's specified in the device tree.
No, currently there is no usage of the device tree directly. So that is actually specified as part of a kconfig option.
Okay. Okay. Well, yeah, just to know.
So I'm just going to pause here. I'm going to end the recording, but please keep going with the questions if you want, and I'm going to hand it over to Kumar from after this point. So thank you, Vincent, for the presentation, and I'm ending the recording now.
Right. Thank you, Vicky.